इस वीडियो में मैं गेट 2023 में एटॉमिक मॉलिक्यूलर में जो क्वेश्चंस आए थे उनको डिस्कस करूंगा. सो क्वेश्चन नंबर 1 फ्रॉम द एटॉमिक मॉलिक्यूलर. सो क्वेश्चन नंबर 1, which one of the following is a dimensionless constant? So option A is permittivity of free space, option B permeability of free space, option C Bohr magnetron, and option D is fine structure constant. So डिस्कस करते हैं इसको. So option A is permittivity of free space, which is epsilon naught. So as we know, k equals to 1 upon 4 pi epsilon naught. This implies epsilon naught equals to 1 upon 4 pi k, and the value of epsilon is 8.85 into 10 to the power minus 12 Coulomb square Newton meter square. So this is not dimensionless, it has dimension. So option B को try करते हैं. Option B is permittivity, permeability. So which is mu naught, and as we know B equals to mu naught divided by 4 pi, and mu naught equals to B into 4 pi, and the value of mu naught equals to 4 pi into 10 to the power minus 7 Newton ampere square, and in another word Henry per meter. Option C is Bohr magnetron, which is mu b, and mu b is defined as E h cross divided by 2 of me, and the value of Bohr magnetron is 9.2 into 10 to the power minus 21 ampere meter square. So this also has dimension. Now option D, fine structure constant. So fine structure constant, that means alpha equals to 1 upon 4 pi epsilon naught E square divided by h cross C, and the standard value of alpha is 1 upon 137. So it has dimensionless quantity. Alpha is dimensionless quantity, so that option D is correct. Now move to the next question. So option D is correct. So move to the next question. Okay, so question number 2, the atomic number of an atom is 6, which is carbon. What is the spectroscopical notation for its ground state according to Hund rule? So discuss करते हैं solution. So carbon, Z equals to 6, so electronic configuration is 1s2, 2s2 and 2p2. So the last two electrons are in p level. So this is the case of equivalent electrons. So the L1 equals to 1 and L2 equals to 1, which is same. S1 equals to 1 by 2 and S2 equals to 1 by 2. Okay, so as we know, the resultant L equals to L1 minus L2 to L1 plus L2, so that L equals to 1 minus 1 to 1 plus 1, which is equals to L0, 1 and 2. Similar for spin, S1 minus S2 to S1 plus S2, so that 1 by 2 minus 1 by 2 to 1 by 2 plus 1 by 2. So the possible S values is 0 and 1, so that we can say the 0 correspond to singlet state and 1 correspond to triplet. Okay, so now the corresponding J values, so make a table here. L values, then S values, then J, then multiplicity which is 2s plus 1, then notation which is 2s plus 1, capital L and J. Okay. So the possible L values, which is 0, 1 and 2, corresponding to spin which is 0, singlet state. So L and J equals to L plus S to L minus S. So 0 minus 0 is 0, 1 minus 0 and 1 plus 0 is of course 1 and 2. So multiplicity corresponding to S equals to 0 is 1, 1, 1 always. So that we can say the notations 1, S equals to 0. So multiplicity is 1, L equals to 0. So that means S and J is 0. Now next is 1p1 and next is 1d2. So corresponding to S equals to 1, there are 3 more values, 0, 1 and 2. So the possible values of J is 1, 0, 1 and 2, 1, 2 and 3. And the multiplicity is 3, 3 and 3 in all cases. Okay. So the notation is 3s1, 3p012 and 3d123. So we get all possible spectroscopical terms and notations are, so that possible terms is 1s0, 1p1, 1d2, 3s1 and 3p012 and 3d123. Okay. So using Hund rule, we can find the ground state notation, but here's some catch, because we are using the equivalent electron case, not a non-equivalent electron case. So if we have such as terms, then we can easily find the spectroscopical terms for equivalent electron using this step. So 1p1, 1d2, 3s1, 3p012 and 3d123. So we can arrange these terms like singlet term are in the one row and the triplet terms are in one row. So now we can choose alternately. If we choose first, then the alternate term is this and this, so that possible terms for 2p2 are 1s0, 3p012 and 1d2. So now using Hund's rule, largest multiplicity lies lower. So largest multiplicity is 3p012. Okay. Now if we have more number more terms having same multiplicity, so in that case we can choose the L values. So largest L lies lower, but L is also same, so we move to the J values. So now we have two cases for J. If less than half filled case and more than half filled case. So if less than half filled, so that 2p2. So the half filled is p3. So this is the case of less than half filled. So in that case, we choose lower J values. So 3p0 is the ground state notation for carbon. Okay, so so option A is correct. So now move to the next question. Question number 3. Question number 3 is an atom with non-zero magnetic moment has angular momentum of magnitude √12 h cross. When a beam of such atom is passed through a Stern-Gerlach apparatus, how many beams does it split into? So given the data is non-zero magnetic moment, okay, and the angular momentum, we know the L equals to small ll plus 1 h cross, so which is √12 h cross. So now L equals to ll plus 1 h cross, so we can say 3 into 4 h cross, so 3 plus 1 h cross, L equals to ll plus 1 h cross. So we get L equals to 3. So now the total splitting due to L, which is angular orbital quantum number. So 2L plus 1, which is 2 into 3 plus 1, which is 7 splitting lines. So option B is correct. So now move to the question number 4. In the vector atomic model of angular momentum applied to atom, what is the minimum angle in degree in integer made by the orbital angular momentum vector and the positive z for the 2p electron? Okay, so इस क्वेश्चन में कुछ नहीं है, डायरेक्ट एक स्टैंडर्ड प्रॉब्लम होता है अपने पास, उससे डायरेक्ट क्वेश्चन था ये. So 2p electron, so in that case 2p electron, so the possible L values is 1, S equals to 1 upon 2, okay, and corresponding ML values are minus L plus L2 minus L. So ML minus 1, 0 and 1, okay. So and the cos theta, the angle between this theta, angle between the L vector and the Z, okay. So ML divided by root of L plus 1, so we can separate it, cos inverse theta ML divided by root of L plus 1, okay. So now this is similar to the space quantization of L. So we have 3 possible values, so that cos inverse for ML equals to plus 1. So 1 into 1 plus 1 multiplied by 1. So theta will be cos inverse 1 upon √2. Then theta is 45 degree. For ML equals to 0, theta will be 90 degree, because 0 L, because L values, so L1 1 plus 1, so theta equals to cos inverse 0, so 0 at 90 degree, and for ML equals to minus 1, so theta is cos inverse minus 1 divided by 1 plus 1. So theta equals to cos inverse 1 upon minus √2, which is theta equals to 135 degree. So now minimum angle between L and Z axis is 45 degree. So this is NET question. So here 45 degree. Now move to the question number 5. Okay, क्वेश्चन नंबर 5 डिस्कस करते हैं. ये थोड़ा ट्रिकी क्वेश्चन था. सो क्वेश्चन स्टेटमेंट जो है वो इट इज द गिवन दैट द इलेक्ट्रॉनिक ग्राउंड स्टेट ऑफ डायटोमिक मॉलिक्यूल विच इज x2 and x2 is unknown for us has even parity and the nuclear spin of x is 0. Which of the following is the correct statement with regards to the rotational Raman spectrum, and the J is the rotational quantum number of the molecule. So option A, line of all J values are present. Line has alternating intensity in the ratio of 3:1. Line of only even J values are present, and line of only odd J values are present. Okay. So क्वेश्चन में कुछ डेटा गिवन है, उसी से हम बात करते हैं अभी. So ground state, which is electronic ground state is even parity, and nuclear spin of x which is 0. ओके. सो अभी इस क्वेश्चन को थोड़ा सा हम क्वांटम मैकेनिकली ट्रीट करते हैं. अगर हम इसको एटॉमिक के बिहाफ पे करें तो माइट भी हम गलत कर सकते हैं इस क्वेश्चन को. सो क्वांटम मैकेनिक्स से हम जानते हैं, सपोज एक वेव फंक्शन है हमारे पास. सो वेव फंक्शन की दो कैरेक्टरिस्टिक होती हैं, या तो वो इवन होगा या ओड होगा, लाइक या वो सिमेट्रिक होगा या एंटी सिमेट्रिक होगा. सो इन दैट केस वी हैव टू वेव फंक्शन फॉर इलेक्ट्रॉनिक स्टेट and wave function for nucleus using Born-Oppenheimer approximation. Okay, so wave function for electronic is symmetric, and the nucleus depends on the various parameter, which is psi nucleus equals to psi translational, psi rotational, psi vibrational, and psi nuclear spin. So translational is always symmetric, vibrational is always symmetric. Okay, because with the respect the interchange of the identical particle. Okay, either can we say the symmetric with the respect the reflection at the center of symmetry. So इस बिहाफ पे हम बोल सकते हैं, because for vibrational we can say V equals to 0 for ground state. Now the changing variable on changing wave function are rotational and nucleus. Okay, so psi rotational has two cases, which is symmetric and antisymmetric. Okay, so symmetric for even J values like J equals to 0, 2, 4, 6 and so on, and odd values of J which is J equals to 1, 3, 5 and so on. Okay, now similar for the spin. Symmetric and antisymmetric. Okay, so symmetric for two spin system, and we take I equals to 1/2 for H2 molecule. Let's say H2 molecule. Okay, So two spin system I equals to 1 by 2. So let's say quantum number related to I, which is mi, so -1 and +1. Okay, so nuclear spin psi nuclear spin corresponding to, like, we have two variables, so mi equals to 1 by 2, let's alpha, and mi equals to -1 by 2, let beta. Okay, so for psi spin, nuclear spin, we have four possibilities. This is alpha 1, alpha 2, beta 1, beta 2, alpha 1, beta 2, and alpha 2, beta 1. Okay, so these two are for symmetric and these two are for antisymmetric. Okay, so that for symmetric case alpha 1, alpha 2, beta 1, beta 2, 1 upon root of 2, alpha 1, beta 2 plus alpha 2, beta 1. So these three cases for symmetric, and for antisymmetric 1 upon root 2, alpha 1, beta 2 minus alpha 2, beta 1. Okay, if we change the coordinates, so we get extra factor which is minus, so we can say that this one is antisymmetric. Okay, so for boson the wave function should be symmetric, and for fermion the wave function should be antisymmetric. Okay, so we already know the hydrogen is fermion particle. Okay, fermion particle. Now for hydrogen H atom is fermion. Total wave function is antisymmetric. Okay, so that we have J levels here. So J equals to 0, J equals to 1, J equals to 2, J equals to 3, J equals to 4, J equals to 5, and J equals to 6. Okay, so this is symmetric, this is antisymmetric, symmetric, antisymmetric, symmetric, antisymmetric, and symmetric. Rotational levels are there. Okay, so here nuclear spin, so nuclear spin for J equals to 0. So now the total wave function for H atom, which is fermion, is antisymmetric. So in that case, if J equals to 0 is symmetric, then nuclear spin must be antisymmetric. This is symmetric, this is antisymmetric, this is symmetric, this is antisymmetric, symmetric, and antisymmetric. Okay, so if we multiply them, psi rotational and psi nuclear spin, so we get antisymmetric, or in all case we get antisymmetric wave function. Antisymmetric wave function. Okay, so similarly, if we have zero spin, so case of zero spin, like oxygen, which is 8, 16. Okay, so I equals to 0. So in that case, the total wave function must be antisymmetric. Okay, so in that case, the psi electronic is antisymmetric. Electronic ground state is antisymmetric in generalized case, so that psi nucleus is symmetric. Okay, so we have some levels again: j equals to 0, j equals to 1, j equals to 2, j equals to 3, 4, 5, 6 and 7. Okay, so this is symmetric, antisymmetric, symmetric, antisymmetric, symmetric, antisymmetric, symmetric and antisymmetric. This is rotational levels. So the nuclear spin, so antisymmetric, symmetric, antisymmetric, symmetric, antisymmetric, symmetric, antisymmetric and symmetric. So if you multiply the rotational psi of rotational and psi of nuclear spin, so we get the antisymmetric function. Okay, so here the antisymmetric states are given by 2i plus 1 and multiply by I, which is I equals to 0. So total the antisymmetric states are 0. So antisymmetrics are 0, 0, 0 and 0. Okay, and for symmetric state, which is 2i plus 1, which is 1. So here 1, 1, 1 and 1. Okay, so in that case we have case of zero spin, nuclear spin, zero nuclear spin, and the electronic ground state is antisymmetric. So the psi, the wave function of nucleus, is symmetric. So in that case, the antisymmetric states are not available. So in that case, we can say these states are not present. These are absent. Okay. So we can say in case of psi electronic is antisymmetric and psi nucleus is symmetric. So the j equals to odd values are present. But in the beginning of the question, they clearly mention the electronic ground state of diatomic molecule X2 has even parity, so that the wave function for electronic state is, so in this question, the psi electronic is symmetric and the psi nucleus is also symmetric. So the complete wave function is symmetric. So in that case, the j equals to even values are present. Okay, so option, so that option C is correct. So move to the last question, question number 6. क्वेश्चन नंबर 6. सो क्वेश्चन नंबर 6 जो है ये एक मिक्सचर है ऑप्टिक्स और एटॉमिक मॉलिक्यूलर का. सो इस क्वेश्चन का जो स्टेटमेंट है, विच इज़ द डिफरेंट स्पेक्ट्रल लाइन ऑफ बाल्मर सीरीज ट्रांजिशन n to n and n along the principal quantum number. Okay, so for Balmer series, we can say 1 upon lambda equals to r infinity 1 upon ni square minus 1 upon nf square. So okay, and we can directly note it down. 1 upon 2 to the power 2 minus 1 upon n square. So 1 upon lambda equals to r infinity 1 upon 4 minus 1 upon n square. Okay, so here the lambda is 4n square divided by r infinity n square minus 4. Okay, so this is our lambda using the Balmer series. Now the spectral lines are falling on a time on Young's double slit apparatus. The separation between the slit, so we can make the apparatus for the Young's double slit. So these are the slits. This is S1 and this is S2. The distance between the two slits is small d, and the distance between the slits and the screen, this is our screen, here we observe some pattern. This is capital D, and in this case it is constant. Okay, so now the what factor should D be multiplied by maintain a constant fringe width for various lines as n taken different allowed values. So we already know using Young's double slit the fringe width is constant. So and we can say the fringe width is same, and the formula for fringe width is beta equals to lambda capital D by small d. Okay, so the small d is the distance between the slits and the screen, and the small d is the separation between the slits. So equation number 1 and equation number 2. So using equation number 1 and equation number 2, we can say that beta equals to lambda, and lambda की value put करना है हमें. So capital D by small d, and what is the equation number 1? 4n square. So 4n square divided by n square minus 4. Okay, and the 1 upon r infinity is there. So beta equals to capital D by r infinity 1 upon small d n square minus 4 divided by 4n square. Okay, so d is fixed, which is constant, and also the r infinity is constant. So these are the constant quantities. So we can say beta is directly proportional to 1 upon d n square minus 4 divided by 4n square. So now the statement of the question, what factor should d be multiplied by the maintain a constant fringe? So the multiple of d is here n square minus 4 divided by 4n square. So this is the option A. So correct option is A. Option A is correct. Okay, so thank you.